vector field. Now it just looks like a mess, but if you rotate it, then that's not helping your head. Sorry. But the idea is you can have kind of this radially outward pointing vector field in a three-dimensional sense, or whatever kind of vector field you have. So you can have two-dimensional versions, three-dimensional versions. Also, we talked about how gradient fields are going to be kind of a big important class of vector fields that have a lot of nice properties that simplify things for us in what we'll be doing shortly. So gradient fields, again, that's just if you have a function f, so if you have, for example, fx comma y is equal to, I don't know, how about this x squared y? Well, what's the gradient of f? Two x y is the I plus x squared j, right? So if you think about it, if you start with some function f, and you take the gradient of it, you get a vector value function. We've got the output of this is an I and a j. So, so that's going to be one important class of fields. Now, something to just refresh your memory on, because it'll be important soon. Gradient vectors and level curves go together in a certain kind of way. If you've got a level curve of a function here, so let's say this is z is 1, z is 2, z is 3. If you're at some point on this z is equal to 2 curve, how would the gradient at this point be facing? It would be facing orthogonal to the level curve that it's on and pointing in the uphill direction, so to speak, right? So you can imagine that when you've got these gradient fields, if you had all the level curves of the function, you could kind of imagine what the gradient field would look like. You'd have all of these orthogonal vectors pointing in the uphill direction, right? So just another example over here. So here's an example of what I've got here. Now it's colored in and shaded, but think of these as level curves of a function. And here are the gradient vectors sticking out orthogonal from those level curves. So not every field is a gradient field, but we'll find out later that when we've got a field that is a gradient field, that's usually really convenient to us and simplifies the stuff that we're doing. Okay, so that's the kind of thing that we were looking at yesterday. And then we started talking about this problem where I ask you to imagine that you've got a velocity field for a stream. So this velocity field, this is just saying how fast and in what direction is the water in this stream flowing at each point. And you could imagine that if you threw something like a cork into this water that's going to just kind of float along, that if you threw it in here and it landed here at time 0, that this would flow along and we can kind of see where it's going, right? So this is an example of, this is called a flow line of the field. So this flow line has to do with an initial condition, kind of where the particle is at time 0. And then particle has no propulsion of itself. It has no choice but to just kind of drift along, doing whatever that vector field is doing. And we should be able to come up with a parameterization for where this cork is in the water at each time. Furthermore, I said that we threw it in here at time 0. A lot of times I phrase it that way. But we can imagine, well, maybe it was floating along all the time, and here's where it was at time 0, but it was somewhere before we started the stopwatch, right? So time -1, okay, we haven't started the watch yet, but we should be able to come up with a flow line for this. Furthermore, how many flow lines are there for this field, do you think? How many places can you throw a cork into this water and watch it float along? There there's an infinite number, right? You could have all kinds of different flow lines that correspond to different, okay, that doesn't look very realistic, that correspond to different initial conditions of where the cork was at time zero, so to speak. So if you talk about all of the infinite number of flow lines for a field, that overall is called the flow of the vector field. So a flow line is one of these guys. If you had, kind of all of them, infinitely many of them, then that would be called the flow of the vector field, the collection of all flow lines. And so what we're looking at is, how can we figure out, given some kind of a field, so given some kind of a field here, so here's a vector field, kind of this radially outward vector field, and you can imagine this cursor is showing where the cork is at time zero, and you can see the flow line corresponding to that initial condition going out through there. Right? So what we want to be able to do is, for different kinds of vector fields, we want to be able to come up with a parameterization for the flow line given some condition. So how do you do that? Given a field formula, how do you come up with the flow? Well, the basic idea comes from, again, imagining this cork floating along in the water, that if the cork is here at time zero, the idea of this cork floating along is that the cork is always going to just do exactly what the water is doing. In other words, whatever the velocity of the water is at this location, that's going to be the velocity of the cork when it's at that location. If a little bit later it's over here, well, now we've got a different velocity vector for the water, and whatever that velocity vector is for the water, the cork is going to have the same velocity vector. So if you want to be really technical about it, this cork that's floating along has to be kind of a almost massless kind of a cork. But that's the idea, that whatever the water is doing, that's what the cork is going to do. So, based on that idea, let me just write up some of the things that I've been saying, and this is 17.4 that we're in now. So, again, a flow line, and this gets called different names. Sometimes it's called an integral curve, or a streamline. Those are just other words for the same thing. So we can say, like, the path a cork would take if it was thrown into a stream. So the stream we're thinking of as a vector. The flow of a vector field, again, that's the collection of all of the flow lines. And so in some problems, we'll be given an initial condition where the cork is at time zero, and we'll be asked to find the specific flow line that goes with that initial condition. Other times, we're not given an initial condition, and we're asked to find a very kind of general type of equation that tells us about the flow of the vector field. So that'll be one that has some parameters. So here's the idea. If we're going to, so we want to find a flow line, and what we've got here is we've got R of t. This is the location of the cork at time t. And this is what we're trying to find, right? This is the goal, is we want to find this. So our goal is to come up with R of t. Well, based on that, if F is equal to the field, what would this composition be? So F is the field. Well, what are we plugging in? We're plugging in the location of the cork. And what are we finding out?
Field?
Yeah, we're finding out what the field is at that place, right? So in other words, you know, here's where the location of the cork in the river. F of R of t tells us, well, what's the velocity of the river at that place where the cork is currently floating. So this is, we could say the velocity of the stream at the cork's location. So R of t's location, F of R of t, that's the velocity of the water at that location. And furthermore, what would R prime of t be? Yeah, this is the velocity of the cork. Okay, so R of t is the location, R prime of t is its velocity, and F of R of t is the velocity of the stream at the cork's location. Now, based on this idea, the cork is going to do whatever the water is doing. What kind of an equation could we set up here?
F of R of t equals R prime of t.
And there it is. That's the equation that we need to solve in order to figure out these flow lines. So the idea is that the velocity of the stream at the cork's location is going to be equal to the velocity of the cork when it's at that location. So, in other words, F of R of t is equal to R prime of t. So what we want to do is, when we're finding the flow line, what we're trying to do is we're trying to find this parameterization, if you like, R of t, that satisfies this equation. That if I plug that parameterization into the field formula, that that's equal to the derivative of that parameterization. Okay? So, I think one of the hard things about this, one of the things that I always found hard anyway, was just kind of some of the notation at first. And so I'm going to try to break the notation down to give you a good way of looking at it. So here's what we got, is if we have F is equal to some function F1, you plug in an X and a Y location, and that tells you the I component of the field at that location. And then you've got some other function of X and Y. And when you plug an X and Y into that, it tells you the J component of the field at that location. So, for instance, this guy over here, if we're talking about this field, this gradient field, this guy would be like F1 of X comma Y. It tells us the I component of the field at a given X, Y. And this guy would be F2 of X comma Y. That tells you the Y component and J component.
Is that supposed to be a V right next to F?
This was originally supposed to say gradient to that. So, if we have some fields, one function tells us the I, another function tells us the J. And what we've got is R of t. This is the parameterization. This is what tells us where the torque is in the stream at a given time. And this is what we're ultimately trying to find, is what R of t is. But R of t, whatever it is, we can assume that it's some function x of ti plus y of tj. So this is what we're trying to find, and it's a function that you plug in a time and it'll tell you what the x location of the cork is in the water and what the y location of the cork is in the water. So we've got this position vector parameterization form. So then what we've got is the flow line that we're looking for is the solution to a differential equation. Now, without a differential equation, class, there's only so many of these that we can solve, right? Differential equations, there's many different types, and they require different techniques. But we can solve some basic ones. So the differential equation is really a system here. What we've got is this. We've got x prime of t. That is, what does x prime of t represent? Yeah, so x of t tells you the cork's x location. X prime of t tells you the velocity of the cork in the x direction, right? The x component of that velocity. And what's that going to be equal to?
What is x and y?
Yeah, it should tell you, it should be the same thing as this, which tells you, well, what's the velocity of the water at that point. So in other words, now here's the only change, is we're going to say f1 of, here it said xy, but now what we're talking about is our x's and y's are really functions of t, right? At different times, the cork's at a different x and y. So over here, we're going to say f1 of x of t, comma, y of t. So in other words, if you plugged in a time, that would tell you the location of the cork, and then plugging the location of the cork into this guy, this would tell you the I component of the stream's velocity, and the I component, so to speak, of the particle's velocity would have to be the same. So what we now have down here is y prime of t is going to be what? Same thing, but with f2. So we're just kind of keep on going with this idea of making the velocity of the cork the same thing as the velocity of the stream at its location. Now, here's the bit of notation that that somehow I always found confusing when I was learning this. So the idea here is, what's going on at this stage is we're replacing all x's and y's in f1 and f2 with x of t and y of t. Once again, that's because this guy here, it says, tell me a location x comma y. But now our location is something that's changing with time. So we've got that composition. So all of these x's and y's now become, oh, x is a function of t, y is a function of t. So the idea is, if we have a field, we can start off with r of t is some generic x of t, y of t kind of formula. And then we can set up a system of differential equations like this. And if we can solve this system of differential equations, then the answer that we come up with is, what did r of t have to be to satisfy this system? Furthermore, if we know an initial condition of like where the cork was in the water at a given time, we should be able to then find out the specific flow line for the situation. So, let's start with this one. Let me turn the projector on. It's nice to be able to see the visual that goes along with this stuff. So the first one is a nice simple field diagram that F is just going to be, even though F we normally think of as a function of x and y, the velocity of the field, the velocity of the stream varies on the location in the stream. This stream is very predictable. So in this stream, the water everywhere in the stream is going the same velocity. So the water is moving along, feel better, have a good 3-day weekend. The water everywhere is going along So, again, this doesn't have arrowheads on it, but you should imagine the arrowheads are all pointing this way, right? Every location in this stream, the vector is going 3i plus 4j, 3i plus 4j, right? Well, so this guy here, oh, and I'm sorry, I forgot to write the initial condition. So we want to find the streamline. How about this? With initial condition that the cork is at location 1, 2 at time t is equal to 0. Okay. So there are an infinite number of possible streamlines, but we've narrowed it down to one particular one. Well, you should be able to kind of visualize what that looks like, because this is a really, really simple field. So the idea is, at time 0, the cork gets thrown in at the location 1, 2, so somewhere up here, right? Well, what shape is it going to flow along in? It's going to flow in a straight line, just following along, going with the flow, right? So what we should find for this guy, this very simple situation, is that the flow line really is a line. And what we should find is the flow line is a parameterization of a line, and we should find that it goes through the point 1, 2 at t equals 0, and it flows in the direction of all of these vectors. Make sense? Okay, so let's set up and solve the differential equation and come up with our answer. So what we've got here is we're saying, okay, R of t, the thing we're trying to find is something like this. So let R of t equal this generic kind of parameterization. Now what we've got is what? X prime of t is equal to f1 of x of t, y of t, and y prime of t is equal to f2 x of t, y of t. Well, what's f1 and what's f2 here? Yeah, so here, these are extremely simple because there's no x's or y's in it, right? They're just constants. So this guy here, we wind up with a really simple kind of situation. So we've got x prime of t is equal to what? And y prime of t is equal to 4. So typically, usually you have x's and y's here, and so typically you have some kind of function of t by the time you do your composition and get down here. But in this case, we've got something nice and simple. So, well, this is a differential equation that's really nice. We can just kind of integrate things to solve it, right? No special techniques needed. So this says x of t is equal to what? 3t plus some kind of constant, right? So I'm going to just call this x naught for now. And then similarly, y of t is just going to be equal to 4t plus y naught. So right here, yes?
Is it simple numbers because we have like straight lines, and since it's like
So it's essentially because the velocity field, since it's just a constant velocity field, that's why we have the straight line. That's why down here there were no t's in this guy, and that's why it becomes so simple over here. So hopefully it's not more confusing to start with a simple example. Sometimes that's the case. Yeah.
I was wondering why, how can you call F1 and F2 instead of just like, because isn't it the same function? It's just like some other function?
No, because what we're saying is F1 we can think of as being one function that tells us the I value and another function that tells us the J value. So a lot of times, even though, we can say F is just 3i plus 4j, for the purposes of breaking this down and kind of being able to notate it and explain it, it's nice to break down F into, well, it's one function that tells me the I and one function that tells me the J. You combine them and you get F. So I'm just breaking that into pieces so that it's easier to see the process.
So you're saying that I and J components have their own I and J components?
No, what I'm saying is this. So you're right that F is just one kind of function, in this case 3i plus 4j. But for the purposes of what we're doing here, we want to be able to refer to just this part that tells us the I. We want to be able to refer to that as kind of its own thing that we're going to put here equal to the x prime of t. Same thing, whatever goes here, essentially that's going to become whatever is going to transform into whatever the y prime of t is equal to. So for the purposes of just breaking it down and seeing, oh, this piece is kind of going to go there, this piece is going to go there, I'm referring to F as being F1i plus F2j. So what we've got right here, this is not our flow line yet. It doesn't go through 1, 2 at time 0, right? Now it'd be very easy to bring in our initial condition and to solve this guy, and I'm not even going to go through the steps of solving this exactly. Plugging in t is equal to 0 here, we find that x sub 0 should be times 0 at location 1. And then y of t, that's going to be what? So, this guy here, so this is kind of our R of t, if you like. R of t would be 3t plus 1i plus 4t plus 2j. Sorry, things are getting a little squished in here. Let's see. Does this make sense that this, the derivative of R of t, R prime of t, is it equal to our field? Oh yeah, 3i plus 4j would be R prime of t. So yeah, it satisfies that. And is the cork at the proper location? Yep, at time 0, it's at 1, 2. There you go, we got it. So if you were to, oh, this is from the days of old technology, remember these? That's quaint. Hopefully I don't get all kinds of crazy reflections. So superimposing this, here's the flow line that we just parameterized. Here's the location of the cork at time 0, it's at point 1, 2. And as you plug in times greater than 1, you'll see that it flows along this way. If you put in times before time 0, you'd find that the particle was back here at earlier times. Okay. questions?
What if
Okay.
they,
Yes.
what if they don't give us a T0? Are we gonna be not
So,
have that?
so you're saying like if you were given a T1 or if you're just not given any initial condition?
Yeah, a T1 or not initial anything. Because isn't it T0 means that when we plugged in the point, it's our intercepts basically for the Y and X function?
Right, and that's why it's convenient if we have T is equal to 0 is our initial condition, because it makes finding this so easy that I didn't even show where.
Exactly.
But if it had been time 1, then I would have plugged in a 1 here and a 1 here and figured things out. But this brings me to another point, which is this. What we found here, this guy is, whether you write it in this form or in the RFT form, this guy tells us the specific flow line that goes with the cork being at 1, 2 at time 0, right? This, though, right here, this kind of general formula, guess what this is? This is the flow of the vector field. It's a general formula that says, you know, wherever the cork is starting, right? This is what the flow line for that is going to be like. So in other words, this guy kind of represents all of the possible flow lines that you could draw on that chart, whereas this one represents the specific flow line that goes with our initial condition. So if you're given an initial condition, you can come up with the specific flow line. If you're not given an initial condition of where the cork is at a starting time, then what you can still do is you can find the flow, which is a general formula for what flow lines are like.
So basically, if you plug in the xt and yt back into the position function, and you end up with a vector formula, a vector function with rt to that whole position in a vector function.
That's correct. And that would tell you what the field is, it's kind of covered up here, but our f of RFT, that tells you what the velocity of the stream is at the location the cork is at time t. Yeah, that's right. One further thing is, so here we've got the flow line in kind of a parameterized form, but sometimes we want to, sometimes it's convenient to know what does this flow line look like in terms of y as a function of x or something like that. Now, if the particle is going back and forth, left and right, then it might not fit into that y equals f of x kind of format. But, let's see, let me, I really want to erase that. Well, actually, this is kind of good. Forgot I had it written on this slide. So our flow line was parameterized this way. But we could also say it's the line y is equal to 4/3 x plus 2/3. This guy doesn't tell us where the particle is at a given time, but the graph of that line is in fact